Hello and welcome to yet another insightful step in our journey to learn the Go programming language and master it. In the previous section, we spoke about applications that can communicate via communication layers and serialization protocols. In this section, we will take that up further and talk about web applications. This section will be rich with examples and contents that we will need in order to master web applications in Go. We will learn to write web applications using Go's standard libraries along with some third-party libraries that are popular in the software industry. We will build web servers, web clients. We will practice building a RESTful API. We'll cover key topics like templates, writing a website backend, and we'll conclude by writing a chat portal for the Hydra software system. Moving on to the first video, we'll start this section by discussing how to write web servers in the Go language. So we'll begin by briefly defining web applications, and then we'll move into some important building blocks like servers, routers, requests, and responses. Then we'll conclude by covering how Go handles URL queries. So what are web applications? Web applications are what powers the internet as well as most of the modern software systems. The architecture for web applications is simple. Web clients, which could be anything, communicate with web servers. A web client must have an internet browser, like Firefox, for example, or just a standalone application. Web clients send requests to web servers via the HTTP or HTTPS protocols. HTTPS is just a secure version of HTTP. HTTP runs on top of TCP, so there are network sockets involved. So for example, when you open a web browser and request a web page, the browser will send a request to the web server hosting this web page. Then the server will respond with the page you requested. So let's discuss the HTTP protocol a little bit. So the HTTP protocol consists of two types of messages. The first type is called an HTTP request. The second type is called an HTTP response. So we send an HTTP request from a client to a server, and then the server responds with an HTTP response back to the client. The HTTP request includes many fields, but for the purpose of building web applications, there are three main pieces of information that we need to know about when it comes to the HTTP request message composition. So the first thing we need to know about is the methods field. So the method fields in an HTTP request indicate the purpose of the request. So if the method is get, then we know that the request is asking the server to obtain some kind of resource. If the method is post, then we know the request is asking the resource to add some data. Another piece of information included in the HTTP request is the URL address. The URL address is basically the address to which we're sending the HTTP request. Then there are the headers. Headers are a list of fields that are used to describe some metadata related to the HTTP request. Like for example, the web browser type who send the request, the host name, stuff like that. Now let's talk about the HTTP response. So the HTTP response message typically looks similar to the HTTP request, except that some fields are missing and other fields are added. So the two main pieces of information that I would like to mention here regarding the HTTP response message composition are the status code, which is basically a code indicating the result of the operation, whether the request was successful or not, for example, whether there were any issues, stuff like that. And there are also the headers, similarly to the HTTP requests. The HTTP response doesn't have methods because it serves as only a response to an incoming HTTP request. So the key to writing web applications in Go is the HTTP package. So the HTTP package has what it takes to write advanced web software. For web servers to listen and wait for incoming HTTP requests, we call listen and serve, which we can find here. The listen and serve function takes two arguments. The first argument is for the address for the TCP connection at which we are listening for incoming connections. And the second argument is an object called handler, which will decide what to do with incoming HTTP requests. So this example right here shows us how we can use listen and serve. So one of the fastest ways to write some handler code is to write a function like this with the signature. Takes two arguments. First argument is an HTTP response writer. The second argument is a pointer to a request. The type of function which has the signature is called handle func. We can then call another function called http.handlefunc and then assign the function that we wrote with a special signature to a URL address pattern. So this line of code simply attaches this functionality to this URL address on our web server. Then when we're done defining our handler using the handle func function, we then call http.listen and serve at the end with the TCP address for which we're waiting for connections, and the second argument we will leave it as nil. The reason why we leave the second argument as nil is because when we define handlers using http.handlefunc, NetHTTP package defines a default handler for us with the requested mappings between URL addresses and functions. So when we have a default handler defined for us, we don't need to pass anything here. We'll cover that in a little bit more details in this video. So before we get into code, let's discuss some important building blocks in the HTTP package. The response writer type is responsible for constructing our server response to a web request. So that is basically the type representing an HTTP response. We can see here that the response writer type includes fields for headers. Those fields represent HTTP headers. And there's also a write method so that to implement the IO writer interface. And this write method could be used to write some data into the HTTP response we're sending back to the client. And we can write a status code in our HTTP response by using the write header method. An important remark here is that because the response writer interface includes the same write method as the IO writer interface, then that means that the response writer type could work with a lot of other packages in Go that support the IO writer interface. So how does Go handle HTTP headers? It handles them through a type called header, which is simply a map. The map hosts the header names and their values. The header type supports a bunch of methods which we can use to add headers, delete headers, get headers, and set headers. So setting headers basically change a header value. We will use the header type in the next video and see it in action. Now let's discuss another very important type, which is HTTP request type. So the request type is the Go object which represents an HTTP request being sent from a client to a server. It's a struct which contains all the information you need to dissect incoming HTTP requests. So for example, we have a method string which represents the method enclosed in the HTTP request. So if it's a get HTTP request, this method value would be get. The URL field represents the URL address of our HTTP request. URLs in Go are represented by a type called URL, which belongs to the URL package. So if we go there, we see here that the URL type exposes all the information within an HTTP URL. So an HTTP URL typically looks like this. So that's the generic form of a URL. In case of HTTP, the scheme would be HTTP, and then the host would probably be the web address we're trying to access, and then the path would be the web page within our web server that we're trying to access. So for example, if we look at the address of this page, so this is a URL address right there. So the scheme would be HTTPS, golang.org would be the address or the host, and / pkj / net / URL and so forth are basically our path. The fragment at the end, which is prepended by the £, represent a fragment in our web page. So for example, in this web page, we targeted the URL section, which is considered a fragment of the page. So all this information is enclosed here in the URL struct, and that helps us dissect the URL address very efficiently. So we have scheme, we have the fragment, and so forth. The HTTP request object also includes a header field, which will host all the headers of our HTTP requests. So that's how they would look like. Basically metadata describing some properties of our HTTP request. The request will also include a form field, which will host data being sent to us from the client. Forms are special ways to communicate data via HTTP, and we will see how to use them in this video. So now it's time to explore some code. So first, let's look inside a folder called HydraWeb, which is underneath the Hydra folder. Underneath, we would have a file called hydraweb.go. Let's explore this file a little bit. In there, we would define the package as HydraWeb, and we would import a bunch of other packages for us to use. So for the time being, we would use the Hydra logger to log into the Hydra log file. We use FIMT, we'll see how shortly, we will of course need to import the net HTTP package, which how we would write our web code, and then a log package in case we need to log some results in the standard output. So let's explore our code here really quick. So we'll write a function called run, and in there we will start by assigning a handler to a URL pattern or a URL address in our server. So in this case, let's say we want to assign a function called sroot, and as you can see here, it follows the function signature required in order to be allowed in the http.handle func. And for sroot, it just gets an instance of the logger. It writes to the HTTP writer, which is basically the response to the HTTP request, a welcome message. And the reason why it could write to the HTTP response this way is because, as we mentioned earlier in this video, the HTTP response writer supports the IO writer interface. And since fimp.fprintf takes an IO writer interface as a first argument, this code will become valid. And that's how easy it is, thanks to the IO writer, to write some data in the HTTP response. We'll then end the function by writing that we received an HTTP GET request to root URL. We will log that to the Hydra log file. So if we dig deep inside handle func, http.handle func here really quick, we see here that it takes two arguments. One is a pattern, which is basically the relative URL path in our web server. The second one is the handler. And as we mentioned earlier, the handler is just a function which takes the response writer and the HTTP requests as arguments. Now, as we mentioned earlier, when we use functions like handle func, a default server handler or multiplexer gets used from the HTTP package. So the file I'm looking at right now is server.go, which exists in the HTTP Go package. And because of this default handler, I don't need to pass another handler when I call http.listen and serve, which is why the second argument is nil. Let's review that really quick. Writing web application in Go is quite easy. You start by writing a handler function like this. It has to have the signature. It gives you access to the HTTP response object and the HTTP request object. Then, once you write your function, you map it to a URL relative address using http.handle func. And then, when you're done, you call http.listen and serve to start listening on an address. Let's go inside handle func quickly, just for a quick remark. So the reason why using the HTTP package default server mux is convenient in a lot of cases is because it does a lot of hard work for us. It does URL string pattern recognition when comparing requests received with pre-saved patterns. Now, what if instead of writing a handler function, we'd prefer to write a handle object, or in other words, an object that will act as a handler instead of the HTTP package default handler of HTTP requests? Let's see how to do that. So I created a file called webhandler.go to host our handler object. And then it belongs to the Hydra web package. We will import a bunch of packages that we will be using as we go. And then let's create a type called test handler, which is basically a struct that includes a single field called R. Let's then write a constructor for the handler. So constructor will be called new handler. It will return the test handler object. And we will use struct literals to initialize it. So we'll return a test handler object with a random value on R. Next is a key code that we need to write in order to make our test handler object an actual HTTP handler. To do that, we need to implement a method called serve HTTP, which acts as the HTTP handler serving function. The serve HTTP method is also implemented by the default mux that is used by the HTTP package. Serve HTTP will have the same signature as a typical handle function. So it would take two arguments. One would be our response writer, called W. The other would be pointer to our HTTP request. Inside our serve HTTP function, we will write a quick code to inspect the URL patterns supported. So let's just hardcode a couple patterns. Let's say, so first, the pattern would be the relative URL path of the HTTP request received by our web server. So we can access this information by looking at url.path of our HTTP request. So this is a URL object that we discussed earlier in this video, and this is a path field. The path field should have the string represented the relative URL path, or just like the URL pattern that we're comparing against. So if this is a root path, then we can print this message into the HTTP response. We just print a welcome message into the HTTP response body. On the other hand, let's say if the request comes with /test handle, then we would print a different message. So we would say test handle object with random number, and then we'll print the random number of our test handler. Just like a way to identify that we're invoking the custom handler that we wrote. This code we don't need to worry about. Can revisit it later. But for now, that is a very simple case of writing a handler object where we compare against different URL paths and try to execute different functionalities based on the URL path attached to the HTTP request. So there are two ways to use the object that we just wrote. One way is to attach it to a specific URL pattern from the get-go. We can do that by calling http.handle. Then the first argument would be the URL address pattern, and the second argument would be the handler object that we just created. So we use a new handler constructor. So obviously this limits the functionality a little bit because it would only call the serve HTTP method that we wrote if this URL path came with a request. How does that happen? It's because if we look at the handle code here, we see that we still use the default server mux, which would take our handler and our pattern. A quick sanity check here, just to show how this code works, is to go to the handler interface, which handle a function took as an argument. And you can see here that this interface only supports the serve HTTP method. Because of this, object was able to pass as an HTTP handler. So whenever you write an object that implements the serve HTTP method, it would implicitly inherit the handler interface. and it will be able to work with most of the code in the HTTP package. So as we mentioned earlier, using our handler like this might be a little bit limiting based on what you're doing. So if your code doesn't try to execute an action based on the root URL, like here, then you should be fine. However, in my case, I wrote a switch statement that would try to execute some code in case of the root URL, or execute different code in case of the /test handle address. So for my code to fully execute, instead of only the second part, I need to, instead of passing the handler like this, I need to pass the handler in the listen and serve function. So when I pass the handler in the listen and serve function like that, then I give myself more power, because now the handler that we wrote becomes the default handler that the HTTP package uses for processing incoming HTTP requests. The risk of creating your own multiplexer and handler lies in the fact that with great powers come great responsibilities, because now your handler should handle all sorts of URL patterns and edge cases that happen when processing an HTTP request. So far, the default multiplexer have worked really well for me, the one that the HTTP package provides. So in order for those concepts to make sense, let's run this code and see how it works. So we'll run the version of the code where we assigned the root URL to the sroot function. The sroot function is the one that just shows a welcome message, welcome to the Hydra software system. And then we assigned the /test handle address to the custom handler object which we created. And the custom handler object implements serve HTTP, as we mentioned earlier. It looks at the URL path. If it's root, then it would show the message saying welcome to the Hydra software system. And I added this part which says from the custom handler to identify our custom object as actual responder to the HTTP request. And we also check if the URL path was /test handle, and if it is, we show the random number which we assigned to the test handler in the constructor. So again, as we mentioned earlier, because we explicitly assigned test handle to new handler, then that means that this code should never be triggered. Well, that is because serve HTTP would only be called when the test handle address is requested. Then in our listen and serve, we make sure that the second argument is nil, so as to use the default multiplexer of the HTTP package. So let's run this code. Oh, actually, another thing that I did was creating a folder called test web code, and inside test web code, just wrote a very small program that calls hydraweb.run. So run here, of course, is a function we were just looking at. So it's just a quick test program to test out the code we've written. So going to the terminal, we can run the test web code program using go run, and it seems to be running. So as you have probably noticed, it doesn't return, and that is because of the fact that listen and serve is basically a blocking call. So this function blocks the code, and just keeps waiting for incoming HTTP requests. Now, if we open a web browser and go to the local port that our code is listening on, which was local port 8080, we would see here the welcome message, not of the custom handler, but of the sroot function. So welcome to the Hydra software system, which is the message we passed in here. Now, if we go to the test handle address by doing /test handle, and that's a relative URL, we find here that the custom handler triggers. So what we did was going to this relative address, which triggered the serve HTTP method of the object we passed here. And the serve HTTP method was the one right there, which showed the random number we had stored in our test handler. Looks good. Now, what would happen if we change our code such that listen and serve gets a new handler object in the second argument? And we can also comment that out. I'll leave the first one though to compare the code. So by doing this, we are telling the HTTP package to only use our custom handler object to process requests whenever a new HTTP request comes in. So let's exit out from the previous code session and let's run our code again to run the new code. Now, if we try to visit localhost 8080 again, we find that the welcome message had changed. So the welcome message now says welcome to the Hydra software system from the custom handler. So it used this code while at the same time ignoring that code. So that's how much power Go gives us when writing web applications. If I try to go to the test handle, it should trigger the other message, which highlights the random number. This one. Perfect. So that's how we can write web server applications in the Go language. Now, what if we want more control over our web server? So for that, we need to learn about a type called server, which exposes a lot of functionality that we can use to control our web server behavior. The server type has an internal listen and serve method which we can call to create web servers. For example, we can control read timeouts and write timeouts on HTTP traffic via the read timeout field and the write timeout field. This is very useful if we would like to kill any stale connections to our web server before they hang up our resources. Let's do a quick example on how to use the server type. Let's comment out all the previous code and uncomment this piece of code. So in this piece of code, we construct a new HTTP server object, or to be more specific, a pointer to an HTTP server object, using struct literals. So first thing we need to do is define the address at which this web server is supposed to listen. Then we define the handler which this web server is supposed to use. In our case, we'll use our custom handler. And then we will configure a read timeout and a write timeout. Those two are features that are made available due to the server object. Now at the end, when we're done defining our server, we just call listen and serve. This will in effect run our web server with these features. Perfect. Now let's talk about another practical topic in web programming, which is a query string. So let's visit the Wikipedia page for query strings. You can find it at wikipedia.org/wiki/query_string. Query strings are basically ways to send specific messages to a web server via a string added to the HTTP URL path. A typical URL with query strings looks like this. The query starts here with a question mark, followed by field names with their values. Field names and values are typically separated by the AND symbol, as shown. If you're not familiar with query strings, please take a moment to read this article. Let's decipher a query string in our code. In the HTTP request struct type, there was a field called URL, which we covered earlier in this video. The URL type implements a method called query. Query can return fields and values from the URL provided with our HTTP request. So the query method returns a type called values, and if we look in values, we find that it's basically a map of strings to string slices. This map hosts field names and keys and field values as the map values. Let's explore that in our code. So going back to our code, let's comment out the part where we create a custom server, and let's go back to the default server and multiplexer, and let's explore a new function called query test handler. Query test handler will be used to handle a query string provided with the URL of an incoming HTTP request. So same as other HTTP handlers, the query test handler function must follow this signature. This gives us access to the HTTP response object and the HTTP request object. Now inside our function, first thing we can do is call r, which is our request.url.query, to access the query string of our request URL, and we'll store that in a variable called q. We'll use fmt.sprintf to create a formatted string which shows the values of q, and we'll store the string in a variable called message. Now let's assume the query provided to us looks something like this. So key1 equal value 1. So let's say key1 equals 2 and key2 equals 3, for example. So we have two fields, key1 and key2, and each field has its own value. In order to get the value of a field, we need to use the get method. Get method belongs to the values object, which is basically the type of q. It's a type returned from the url.query method. So by using get, we get the value of key1 and we get the value of key2. We store them in variable v1 and variable v2. Let's compare the two values and output a different message accordingly. So let's say if v1 equals v2, then our message would say v1 and v2 are equal. And then we'll show the value. Since they're equal, we'll just show v1. Otherwise, if they're not equal, we would say v1 is equal to the value of v1 and v2 is equal to the value of v2. Then at the end, we'll use the power of interfaces by utilizing fprint from the print package to write the formatted string into our HTTP response. Perfect. Now in our run function, we will use HTTP to handle func to map the handler that we just covered, the query test handler, with a new address called test query. We should also ensure that the default multiplexer is running here, so the second argument to listen and serve needs to be null. Well, we can also bring back this guy just so that we have 3 different URL paths. So let's run this code and see what happens. So we'll type go run test webcode.go to run this code, hit enter, and it doesn't return, so it means it's working. So now we open a web browser to test out this code. So we go to localhost 8080 where our web server is listening. Then we go to the test query URL address, and then we use a question mark as shown to indicate that there's a query, and let's try to make the 2 keys of the same values. So we have 2 fields here. First field is called key1 with value 1. Second field is called key2 with value 1. So if I hit enter, sure enough, our code works as expected. So first we see a map of the fields and values we passed. So first field was called key1 as shown with value 1 as shown. Key2 is also reflected, and the code where we compare the 2 values also triggered because the 2 values are equal, and the message indicating that v1 and v2 are equal was attached. Let's try a different value for key2, and sure enough our message changes, indicating that now v1 is equal to 1 and v2 is equal to 2. Perfect. Our code works as expected. This was a rich section at which we dove deep into how to write proper web server applications in the Go language.